Velocities.
Thank you. Good morning, everyone. It's a really great pleasure to be here giving the introductory talk to radio velocity. So my talk is, since it's the first of the day, I'll start with basic and easy ones by defining radio velocity and really thinking about fundamentally the question, what we are measuring when we're measuring radio velocities when we're trying to search for planets. And also, I want to get very practical for the audience here, especially that knowing that not everybody will go into the field of radio velocity and really study it in detail. But I hope that everybody will walk out of this talk knowing if they receive a radio velocity data set from their collaborators, what they're looking at, what are the caveats, how you can use it, and have a deeper understanding of the data so that you can better use it. And then I'll go into a little depth about how exactly do we get RVs from the data, hoping that I'll convince you this is a really interesting problem. We're facing some very interesting and unique challenges in the field right now, but we hope to overcome that in the coming years. Just a quick prelim for this talk / lecture in general. I know slides will be publicly available online, so some slides are dense. They're meant to be sort of a lecture type slide packed with information, so you don't have to worry about taking notes or something. But when you feel overwhelmed about the slides, just focus on the larger fonts on the slide. Those are sort of the take-home information on the slides. And this talk focuses on an overview for the RV and sort of from a practical standpoint for users of RV data. So I'll brush off a lot of topics instead of going into depth. But if you're interested, you can ask questions or come back to me or email me after the talk, and I'll provide a list of references at the very end if you're interested in going in depth on some of the topics. All right, let's begin. What is radio velocity? As many of you know, it's the velocity of your target along the line of sight. So, for example, if you have a planet that's causing the stellar wobble, you'll see the stellar spectrum going blue shifted and red shifted, blue shifted and red shifted, and you're measuring this Doppler shift to measure the radial velocity of your target. And the important note to remember is just when the velocity goes positive, the target is red shifted, it's going away from you. So it's just like the Hubble flow in the extragalaxy field that red shifted, everything's going away. That's the way to remember it. All right, now if you really think about the RV component, you have a star far away out there somewhere. You're measuring its velocity along the line of sight. What is in that velocity? What are the components in that velocity? First of all, when you're doing the measurement, you measure the velocity in your lab frame, right? You're measuring its speed with respect to your little spectrograph. That's the thing that you're directly measuring. So the first component naturally is the relative speed velocity between the star and our entire solar system. But then there's also our solar system really means our entire solar system, the very center of our solar system, right? But there's also the relative speed between the Earth and the very center of the solar system. As you know, the Earth goes around the sun. But there's also the component where the Earth rotates and your observatory is on some place on Earth that rotates together. So there are really three components in the RVs. But really what we care about is really just the relative speed velocity between the star and the solar system. So when we actually do data analysis, we correct those two letter terms out. We can calculate them to very high precision, not just subtracting velocity, but taking into relativistic and also general relativistic effects. You can see Eastman and Wright for a very nice paper. This is considered very much a solved problem because the pulsar timing community uses this correction all the time. And they do it to 1 millimeter per second precision. And that's what it takes to detect, things like planets around pulsars. All right, but in fact, if the velocity you care about is really just the relative velocity between the star and the solar system, what you want to do is to shift your reference frame to a barycentric frame, right? To the barycenter of the solar system. You want to make sure your measurement, when you time your measurement, you want to time it for the time when the light arrives from the star at the barycenter of the solar system. And you want the relative speed between the star and the barycenter of the solar system. But even if you consider that, in the relative velocity between the star and the solar system, there are still several components. There is the systemic velocity of the star, which is like sort of the rotation of the galaxy, the random velocity of the star in the sky, right? It's more or less constant in the time frame that we think about things. So that's generally considered just an offset. So if you go to Sinbad, you see the velocity reported for this star. That's typically the systemic velocity of the star. And there is also the velocity of a star around the barycenter of its own system, right? The star itself very often is not at the center of the star. Sometimes is not the barycenter of its system. For example, our sun is definitely offset because Jupiter and other planets in our solar system have met. If the star has a stellar companion or planetary companion or something else, it's offset from its barycenter, and it will have gravitationally induced motion around its barycenter. So this is really the component we care about, right? So we don't care about the motion of the Earth, although it's in our measurement, and we don't really care about the systemic velocity of the star. But fortunately, that's just offset. But we care about the variation of the star in time around its own barycenter. So that's really what we're measuring. There's a lot of things coming in at the same time when we're doing the measurement. All right, so how do we do this? We measure the Doppler shift of the star by measuring the wavelength change of its spectra in time, right? So you take a spectrum of the star at one certain epoch, t equals t0, you have this dashed line, and then you come back at later time, t equals te, your epoch observation, and you have another spectrum, and you can see it's almost definitely shifted. And what you're measuring is this Doppler shift. But something to keep in mind, which is very important, is that very often you plot spectrum in wavelength space, and people like to consider it's a Doppler shift. You shift the spectrum, but it's not a shift, right? Doppler shift in wavelength space is a stretch. So wavelength is the wavelength of the epoch times the wavelength of the zero time, t0 times 1 plus z. So it's not a net shift. You're not adding a constant. You're stretching the spectrum. We are doing it in wavelength space. So that's what we're measuring. We're measuring the Doppler shift from the spectra. You're measuring this using a spectrograph, of course. So in reality, when you're doing this, what you're really measuring is you're measuring a delta RV, the change of the Doppler shift in the star with respect to some arbitrary reference time frame, and you're measuring it in your lab frame, right? That means two things. Very often we're not really measuring the absolute RV of the star because you're measuring Doppler shift with respect to some reference spectrum that you either conjured up with theoretically or measured. So you're measuring the delta RV with respect to some arbitrary offset. So you have this arbitrary RV offset, not necessarily the systemic velocity of the star, but you're going to have some sort of offset. And you're measuring this in lab frame because you're taking data with your spectrograph. So naturally, you need to translate this into barycentric frame. So you're reducing the motion of the Earth, which we'll come back to briefly later. So you need to do barycentric correction, which can be a really tricky thing to do. And some of the first claimed detection of exoplanet were actually due to incorrect correction of the barycentric velocity. So if you do this wrong, you're very easily you get a planet of period of 365 days. So if you get a planet of 365 days, be careful. All right, so now let's think about it, even thinking back a little further. What do we actually measure? If you think about, I'm gonna gather some data, measure the velocity of a certain star. First, you take spectra at different epochs. I'm not gonna cover this part. Sam will talk a lot about instrumentation, and after we'll talk about more on data reduction. I'm not going to talk about how you take spectrum or how you reduce your 2D shell spectral image into a 1D wavelength and flux frame. An entire lecture can be given on that. If you're interested, we can discuss offline. And second, to measure the Doppler shift, you need to measure the wavelength for each spectrum. So your measured spectrum needs to be wavelength calibrated to exquisite precision. 3, then once you have wavelengths for spectrum at each epoch, you measure the Doppler shift between each spectrum with respect to your reference, whatever you set your reference to. And then after you measure this Doppler shift, like I said, you take off the barocentric correction and maybe even the arbitrary offset, and you have a variation of the radial velocity of the star that can tell you whether it has a planet or other companion, or it's just quiet. All right, so according to different style of wavelength calibration, the current methods of measuring radial velocities can be roughly categorized into 2 types. Traditionally, they're iodine-cell calibrated spectrographs and thorium-argon calibrated spectrographs. But these days, the field has evolved. So you may still hear a lot about iodine-cell calibrated and thorium-argon calibrated these days, because they're the most active ones are still using those 2 major calibration sources. But we now have lots of new types of instruments. So now broadly, they're roughly called absorption cell calibrated spectrographs and also simultaneous reference spectrographs. So one example of the absorption cell calibrated spectrograph, which you probably have heard of, is the CARET. So CARET is more or less a general purpose spectrograph, but you can put an iodine cell in, and your light pass through the iodine cell here. This is actually from Lake Hamilton, one of the first iodine calibrated spectrograph, and then it hits your slit and entering the spectrograph. So black is the stellar line, and as the starlight going through the iodine cell, you will have many sharp and narrow iodine lines imprinted on top of the stellar line. And you know the exact wavelength and shape and depth of those iodine lines, and that helps you calibrate your wavelength. It also helps you calibrate how your spectrograph broadens the spectral lines. So this is how you get the wavelength solution of the star and also measure the Doppler shift. And for the simultaneous reference spectrograph, the golden example is the HARP spectrograph, north or south. They are stabilized in their vacuum chamber. So presumably their wavelength solution on the CCD grade doesn't change, at least doesn't change much, or in a very measurable way and predictable way. So sometimes what you do is you feed the object into one fiber and you feed thorium-argon lamp into another, and thorium-argon lamp tells you the wavelength of your pixel grade. And sometimes if your spectrograph is stable enough, you can get rid of thorium-argon, and you just know the wavelength solution will stay on in a certain pattern, and then you get the wavelength solution for each spectrum at each epochal phase, basically, and then you measure the Doppler shift. So now we have those 2 types of instruments to measure the RBs. And once you have taken your spectral, how do we actually get the RBs out? Right, that's actually not a trivial step. So there are roughly 2 types of techniques to extract the Doppler shift information from your reduced 1D spectra. The first is the cross correlation function technique, CCF. It's very, very widely used for stabilized spectrographs, or you may be familiar with it if you just go to a general purpose spectrograph, take a spectrum of your target, and then take a thorium-argon frame before or after, and just get a rough radial velocity measurement. For example, people who study star clusters, they want to measure the systemic velocity of the star, and they want to get a rough radial velocity. That's also the way very often how they do it. But if you are dealing with stabilized spectrographs, you can use this method to get very precise radial velocities out as well. And the second method is more complicated. It's called forward modeling. It can be used for both calibration methods, but it's more often used with the iodine absorption cell calibrated spectrographs, because there you sort of don't have an option. You have a heavily blended spectrum that you want to velocity cells, and cross correlation just doesn't quite work. All right, so Arpita will talk more in depth on CCF, so I'll just briefly introduce it. What is it really quickly? This is from her paper. So you have a stellar spectrum you measured at a certain epoch. And very often what you do is you cross-correlate that with a stellar mask. So a mask is like your little toy model for the absorption line. the depth and the width of those delta functions are designed to match the depth and width of those stellar absorption lines. So you shift your mask to a certain velocity, do a cross correlation, you get a data point. You shift it to a different velocity. In this time, you're getting the right velocity. And then you do a cross correlation, you get another data point in your CCF. And because you're getting the right answer, you're hitting a minima at the CCF. And then you're shifting again away from your true answer, and you're getting another point. So you, in the end, you get a CCF function, and you do some tricks, either feed Gaussian or something, to find the minima, and you have your radial velocity. So fast and simple and elegant. And for iodine calibrated spectrographs, the story, or absorption cell in general, the story is a little more complicated. We use forward modeling. So the goal is to model those black dots, which are the observed spectra. And the observed spectrum has two components, the star, which is black, and the iodine, which is green. And showing here, they are being broadened by our spectrograph already. But before they're being broadened in their native resolution, this is what they look like. So this is your truth, ground truth, your stellar model, or we call stellar template, or stellar reference spectrum, and your iodine model, which we very often call iodine atlas or gas cell atlas. So what you do is you shift your stellar spectrum according to your model for your Doppler shift, and then multiply those two spectra, and then convolve it with the spectrograph PSF, or line spread function, or line response function. There are many names of the PSF for your spectrograph. And you try to match this black dot, right? So in this, you're starting with the ground truth of your spectra, and you push forward to model your observation. And in the process, things like wavelength solution and Doppler shifts, that's part of your model. That's the parameters you're trying to fit. So this is forward modeling. That's how we get velocities out of forward modeling. Just to summarize this gruesome process, you're building a model, and you're trying to fit your observation. The model has two broad components. One is the reference spectral. You have your iodine atlas, or in general gas cell. And you have your stellar template. This is basically a star's true spectrum unbroadened by spectrograph at like an arbitrary epoch. This is your reference time frame. And then you have the model parameters, including your line spread function, how your spectrograph broadens the spectral lines. Those can be very complicated models. And then you have your wavelength solution, the wavelength as a function of a CCD grade, and then also the Doppler shift. How do you shift the stellar template if you multiply it with the iodine atlas? This is the most crucial parameter we want to get out. And this is how roughly forward model works. I just want to say one word about the stellar reference spectrum or stellar template, because that's sort of a key component in both CCF and forward modeling. Knowing sort of the ground truth for your star is kind of key. They're typically empirically derived, first of all, because if you do things like stellar synthesizing or try to extract stellar parameters, when you try to match theoretically synthesized stellar spectra to real observed, you probably know the frustration of they never match when you're talking about high resolution spectra. They, in some wavelength regions, just shockingly do not match at all. So we're forced to derive an empirical stellar reference spectrum. For the forward modeling techniques, especially for iodine cell calibrated spectra, the state of the art is still doing deconvolution. So you go to your spectrograph, take an unskysed spectrum of your star that is being broadened by our spectrograph, and then you deconvolve it with your spectral PSF. But this is a dark art. As you know, deconvolution has no rigorous mathematics solution. So it's a trial and error process that is not easy. And when you do CCF, you can either use a mask, like the delta function I showed you, or you can use a empirically derived stellar template to do your cross correlation. But either way, you are basically empirically deriving it. The masks are very often customized and very carefully built for example, a certain star or certain spectral types of stars. But there's also a way of, if you have many epochs of observation on a single star, you can shift them in the same reference frame and stack them to get a high fidelity stellar spectrum and have that to be your stellar reference spectrum, which is the half-para pipeline that's documented over here. But so the interesting thing is, especially in the recent years, we have realized you don't actually absolutely need them, which is interesting if you think about how it's just the methods I talk about on how we measure velocities, how do we get rid of them? So there are two proposed solutions in the literature so far. They have many similarities actually. The first one is what we call the grand solution. This is especially true for the gas cell absorption calibrated spectra. You have heavily blended lines, but you know the stellar spectrum is shifted back and forth between the lines. So you have many epochs of observation. You can extract the underlying stellar spectrum out of there because you know the true solution for your calibration absorption line. So you grab the information from all epochs and extract the true underlying stellar spectrum. And then in the meantime, you basically just get radio velocities for free. It's actually a pretty algorithmically and computationally challenging process. And you do it sort of iteratively and with many other tricks. But Peter Plachang's group working with seashell in the near infrared actually has gotten this method to work. And Jeff Valenti and also BJ Fulton has gotten it work for Kek-Harris, which is really impressive. And you can see this paper published by Peter Gao. Peter Gao actually wrote the pipeline for seashell in 2016 for details. And another method is put out by Ian Chakala last year called SOAP. I think he wrote it mostly to deal with sp2 double spectroscopy binaries. But he uses Gaussian process to extract the underlying true spectrum, and it's in a template-free way. So those are really cool new numerical methods. All right, just to summarize, how do we get RVs out? We have CCS and forward modeling. They both have their pros and cons. The CCS method is quick and simple. As you can tell, it's very elegant. You just step through in wavelength space. One thing you want to be careful about is that you're not really stepping, right? You have to stretch the spectrum if you work in wavelength space. But it has its drawbacks. This absolutely relies on stabilized spectrograph, because if your wavelength solution is not precisely known, your wavelength grade obviously changes a lot, and then you lose your power of calibration, and you lose your accuracy and precision of your wavelength solution for each epoch, and then you're kind of screwed. But those spectrographs are very expensive to build, but now we know that they're really the way forward. They're the way to go. So all the next generation spectrographs are stabilized spectrographs. It's very hard to deal with spectral contamination, such as telluric absorption with the CCF method. There are ways to deal with them, but they bring things closer to forward modeling, in my opinion. And it's also hard to deal with variations in spectral PSF. Well, actually, the point of building a stabilized spectrograph is that you have a rock steady spectral PSF, right? Your PSF does not change. But if it changes, there's no way you know it. It's really hard to know. Unless you truly do simultaneous calibration. Even that, you can't feed light into your sine fiber simultaneously with your star, so that's hard. Forward modeling, its advantage is that it's very versatile. You build this gigantic model, you can throw whatever you want to it, right? You can throw telluric contamination, you can throw PSF changes, you can throw whatever stellar activity, distortion of lines if you want even. So you can add components and you can deal with the changing PSF. So it alleviates the pressure on building a stabilized spectrograph. You can turn a generalized purpose spectrograph into a 1 meter level precise radio velocity machine, but just sticking a gas cell into it this way. So that's the beauty of it. But it has its drawbacks. Algorithmically, it's very challenging. And if you really want to push to beyond a meter per second, it can become computationally challenging as well. So it's not just doing a simple CCS. You're either doing some least chi-square minimization, or maybe you want to push to Bayesian space, or maybe step through the velocity space, and that becomes expensive very rapidly. Because very often we're doing, for example, the typical models we use for iodine calibrated spectrograph these days have 17 free parameters, and 12 of them are the stinky PSF of your spectrograph. And you're trying to extract one crucial parameter, which is the Doppler shift from all of this. But luckily, they're mostly orthogonal to the Doppler shift parameter, which is the sole reason that this technique works at all. So there's that. All right, just to quickly review, what do we actually measure? We measure spectrum. We measure the wavelength. I've talked about two methods of calibrating the wavelength. And then once you have a wavelength calibrated spectral time series, you measure the Doppler shift. And then you do barocentric correction. So just to give you sort of a teaser and sort of a quick mental concept, which I hope will be sort of the image in your head when you walk out of this room of what this game really involves. A meter per second is roughly, on the scale of today's typical spectrograph, 1,000th of pixel shift on your CCD. But you're not going to be able to do this for any single line. The only reason we can do this is to have hundreds and thousands of lines that we can do a meter per second or even further. So, and the interesting thing is, when you measure the Doppler shift from epoch to epoch, remember, it's not going to be a meter per second shift, even if the star itself in its own reference frame only changes a meter per second. You have Earth, right? The largest signal you're measuring when you're getting a pure Doppler shift out of your spectra is always the Earth. This is roughly how things change on wavelength space. This is 1 angstrom, 1 angstrom, 1 angstrom. And as you can see, as the Earth goes back and forth, your cell line just rasters on your CCD. And if you have an absorption cell calibrated method, it beats against your absorption line. And Earth signal is typically plus or minus 30 kilometers per second. So that's many, many, many pixels across, right? So you're dealing with this thing that changes on your CCD frame on the order of many tens of pixels. And you take the barocentric correction out, and you're trying to measure 1,000th of 50 pixel shift. Fun, fun, fun game. All right, now let's move on to a quick menu for using typical radial velocity products. So suppose you're trying to, for example, validate some test targets, and you got a time on certain RV instruments from your collaborators, and they followed it up to try to validate or confirm the planets for you. And in the end, they finish their observing runs and hand you this radial velocity product and say, go feed your orbit. What are you going to receive? So typically, you're receiving 3 columns, some even maybe more, typically more actually. The 3 most crucial columns are of course time. That's very often in BJD. So if it's not in BJD, you should think it for a second. BJD stands for barycentric corrected Julian dates, right? So some people just use JD. I think that's okay, at least to like a meter, half meter per second precision, that's fine. So the BJD is the time when the star like reaches the barycenter of the solar system, right? The JD you're recording in your header is very often like MJD or just JD. That's when the light reaches your detector. So those are 2 different times. And then the second column is RV in meter per second or kilometer per second. Different people do it differently. But do not be alarmed if you always have an arbitrary constant offset, and sometimes they can be huge, especially for certain groups or the CCF method. They try to get sort of the net systemic velocity out of the star for every single epoch. You can't really get the absolute velocity of the star to precision better than 100 meters per second. That's just because on the atomic physics level, we do not know the absolute wavelength of each atomic line to that precision, but it's going to have some arbitrary constant that sort of stands for either the systemic velocity of the star or just some arbitrary offset because you're measuring the velocity with respect to some arbitrary reference spectrum. But you can just get rid of it, subtract it, or feed it. Then there's the column of arrows. That's the arrow bar on the velocity. This is the most tricky column. You definitely want this column, first of all, but then you have to know what they are. They are very often the internal errors reported from the data analysis process for each single epoch. They do not accurately or precisely represent the overall precision of the spectra most often. In the relative sense, it does. When you compare error bars between instruments or between targets, it gives you a relative sense of how precise each spectrograph or each target is doing, but it's typically just really trying to represent the photon limited precision of your single epoch measurement of the RV, right? Very often, it's underestimated from whatever the overall RV RMS you should be getting if you have a perfectly stable star, because it's very hard to estimate instrumental and stellar jitter. That when you try to feed your data, you do want to fold those in. So there's that. So it represents RV precision in some way, but not really. That's why very often when you go see a paper using RVs to fit orbits, you can see that they have this sigma jitter term that's being added in quadrature to those error bars, and those represents the things that were omitted. We try as observers and data analyzers to best present to you this error bar, but in reality, some of them are just impossible to grasp, right? Things like stellar jitter. All right, now since we're here on arrows, I want to give you a quick overview of what is RV precision. You probably hear people talking about RV precision quite often these days, especially there are over 20 new and commissioning really velocity instruments out there in the world right now, and everybody is trying to shoot beyond the meter per second level or 10 centimeter per second level to detect the Earth analog. But really, RV precision is a very broad term, right? It can stand for, in my opinion, three things. Very often we talk about photon limited RV precision. That's sort of your typical error bar, although the reported error bar has some term from the instrumental jitter, but very often this is like what we're trying to do. This is the best you will ever get because of the information content provided by the star. For example, if you have a rapid rotator, your line is terribly broadened, then there is no way you can get super precise velocity out of the star, right? Or if you have A star, B star, this is why we can't do precise velocity on direct imaging stars, is because they're hot. They don't really have any absorption lines. If they don't have lines, how do you measure the Doppler shift? Almost all of the information of the Doppler shift comes from the slope of the line, right? It's the slope changes on your CCD that you're measuring. And it also depends on the amount of photons you're getting. You're naturally doing better on bright stars, or if you go to longer exposures. And it also depends on calibration methods. Some calibration methods are more efficient than others. For example, if your calibration methods only give you a 2 angstrom chunk that you can work with, you're not going to do as well as, say, HARPS, which has over 200 nanometer wavelength grasp. And then there is the instrument RV precision, which is probably what you hear most when you go to a talk talking about a new RV instrument, and we're going to do 10 centimeter per second or 30 centimeter per second. They're really talking about the intrinsic capability of their instrument, right? This is set by how stable the instrument is, how stable they can put the wavelength solution on the CCD, or the change of the spectral PSF. It depends on your calibration methods. For example, thorium argon is not as good as laser frequency combs because you just don't have that much information from thorium argon. And those lamps change and age and die, and it's terrible. And it even depends on your data analysis method, which doesn't really have anything to do with your instrument, but really, data analysis method can make a big difference. It can really, if you do a lousy job, you may think you're stuck with 3 meters per second. That's very true for many groups in the world in the past 2 decades. But if you just push things a little further, you will actually see that you can actually do 1 meter per second. This precision is often quoted as the goal for new instruments. So when you hear people talking about 10 centimeters per second and 30 centimeters per second for certain spectrographs, this is what they're really talking about, right? Because you're not gonna do 10 centimeters per second in say an hour on a 11th magnitude star, no matter which telescope you're on or which instrument you're on. And there is the actual on-target RV precision. This is what we really care about, and this is what quantifies our ability of detecting planets, digging those little signals out of those vast velocity Doppler shifts. This is naturally set by the two terms above, combination of both, added in quadrature, plus stellar jitter and stellar activity, which is really the elephant in the room for the field of radiolocity today. And there will be talks and lectures focusing on this today, later today. Often when we try to sort of calibrate our instrument and get an idea of how well our spectrograph is working, the true RV capability of our spectrograph, we try to get this on-target RV precision, but it's hard because stellar jitter is mingled in there. So what we try to do is we have a set of favorite RV standard stars that everybody in the field knows. It's like Tau Ceti, Sigma Draconis. There are a few targets like that we consider RV standards. So they are quiet in terms of stellar activity and stellar jitter, so they don't really pulsate like crazy. They do pulsate. And they do not have any known planets, at least not to the amplitude of the current precision. But I suspect those RV standard stars will go away very quickly as we bring our instrument RV precision down. We're gonna start digging out things, hopefully. All right, just a very broad overview of what goes into RV precision. So I talk about those different definitions of RV precision, but if you're trying to establish a spectrograph or a program, and you're trying to hit high precision, here are the typical components that you want to consider to be able to achieve high RV precision, right? They are roughly divided into three groups: astrophysics, hardware, and software. In the astrophysics side, you have your choice of star. You don't want to observe A and B stars and rapid rotators. You have your stellar variation. That includes stellar jitter and stellar activity. Jitter stands for non-magnetic short-term variations, and stellar activity are magnetic related stellar variations. Your ability of dealing with this really sets your RV limit. Hardware-wise, you want a stabilized input. Sam will talk a lot about hardware. You want a stabilized temperature, pressure control spectrograph. You want a really good calibrator, so moving away from thyron argon to laser frequency comb. And if you want to do below 0.5 meters per second, you may not want to use iode and tau, for example. And there's also the software. How you deal with tellurics is very important because, especially in the near infrared, they're really just everywhere. And then how you do a data analysis, that can also make a difference. So you want to make sure you hammer all of this down. So it's like a big tent that's housed by all those 7 components. And if you leave like any single one of them up, you're going to have a large RV error budget, right? Thinking into the future a little bit, we're really heading towards a very bright future in the RV. This is a plot of the first publication date vs the RV semi-amplitude K. Outdated, but roughly represents the idea of, like, you can see our ability of measuring precise velocities steady progress in the past few decades, and then we sort of stuck for a few decades because a couple of decades because we don't have new instruments, and then with a whole swath of instruments, and this is only like a selection of them, we're going to break the meter per second barrier and hopefully get us into the Earth analog regime very soon. This is just selected instruments, but particularly new. That's what NASA is building. It's going to go on Wang, and that will have about 30 centimeters per second precision, and that's going to be publicly available. So this is the most exciting spectrograph in my opinion. All right, let's keep the. Let's maybe talk about this. So we talk about measure Z, the Doppler shift of the from the spectrum, right? So, but if you think about it, Z is really not really the true Z, right? You're just measuring some sort of apparent shift or stretch of the spectrum. So that Z is going to have two components: Z star, which is not really a Z, but the star does all sorts of weird things that mimic a Doppler shift. And then you have the true planet signal you want to recover. For example, if you have some sort of skewed line, and that's going to mimic Doppler shift, right? So in the coming decade or so, we are thinking very hard about how to extract this information from the spectrum instead of dealing with it post-process. So that's something to look forward to in the near future. That's all. Thank you. Oh, I do have lots of references, just so you know. You can find them online.
Thanks for your talk, Sharon. So any questions for Sharon?
Oh, clear. Okay.
Yeah.
That's a good question. Can you please repeat the question? So the question is, how big is the effect of the gravitational redshift caused by the Earth on the incoming photons from the star? Jason, do you have a? Okay, cool. So Jason Eastman, who wrote the barocentric correction code that everybody should use, answered that it's on the order of 3 meters per second, but he's not completely sure. Yeah.
Any more questions? This side there. Come on, don't be shy. Here, great.
Yeah. So the question is, what kind of techniques do you use for near infrared precise radial velocity spectrographs? Because they have lots of tellurics. Do you really even use absorption cells? So Arpita, are you going to talk about some of that? Yeah, so she will. But very quickly, there are absorption cell calibrated near infrared spectrographs. What you do is you offset your gas cell from the telluric absorption. So telluric absorption, historically, which is very interesting, the first concept of precise radial velocity was countered by Griffiths in the 70s using oxygen lines. They countered that you can use oxygen lines as calibrator, and you should be able to do 10 meters per second. That's, of course, very hard, but people did it finally in the 2000s. So, but now we realize that tellurics vary too much, so you don't want to use that in the near infrared. So what you can do is you can use isotopic gas cells that would offset you from the telluric gas cell, because now instead of using C12, for example, in methane, you use C13 and your wavelength is shifted, and you can use it as a regular gas cell. But all the new next generation near infrared spectrographs, they are all stabilized, so they don't really use the gas cell method because it's really hard and messy, and we don't know if it gets you down below 5 or 3 meters per second. We're still trying. Yeah.
Any more questions for? Yeah.
Oh, you're in the know. Tom's question is about normalization of the spectrum, because as you know, the star has an SED, and then when you image it on your CCD, you have a shallogram, and that has Blaze function. From outer to outer, you have this broad envelope, and you're trying to get velocities from not the normalized flat spectral I've been showing, that's the ideal cases, but this curved spectrum, right? If you try to unbend that and stretch that, that's easily mimicking Doppler shift, right? So to a meter per second level, that is not the dominant error source. It's a headache in our data analysis process, especially if you're doing form modeling, you really worry about this. But if you just chunk it up, assume some linear Blaze function for your little chunk, you're good enough to a meter per second level. But for things beyond a meter per second level, it matters a lot. I think, Sam, are you going to talk about that? No? Oh, Arbiter will talk about that. So change in your Blaze function can also introduce instrumental jitter. Yeah, it's a big problem.
Great. Let's thank Sharon again, and
Thank you.
Thank you.